Yeah, thank you, Michael, for the introduction, and thank you everybody for coming to my thesis defense, and also everyone on Zoom. The topic of my thesis is towards high-performance simple models of lake locomotion. This might not mean much to you at the moment, but I will just quickly start with the motivation for the talk first. I want to start by showing you there are many recent startup companies that aims to make humanoid robots. The reason is the humanoid robots show many big promises. Some of the company say that this addresses the labor shortage. It reduces the number of workloads in unsafe area. And the platform is general purpose. So you can go anywhere human goes. You can theoretically do anything that human do. For example, in the home setting, maybe it can help us do the laundry. It can cook for us, buy the grocery for us. So the limit is the potential is really unlimited. But in order to achieve this, there are many technical challenges that we need to address. There are many challenges, and I just highlight two here. So first is the humanoid robots that we see in the previous slide. They all have many degrees of freedom, and the dynamics of the robot is very nonlinear. What's the solution? Currently, most people use a combination of reducer model and model predictive control. The reducer model reduces the complexity of the full model, so we can plan the robot's motion in real time. And one example of the reducer model, probably the simplest one, is linear inverted pendulum. So if assume the robot's point mass and it restrict the center of mass in the plane. And in the planar, we plan the center of mass position and also the corresponding footstep application. And another simple model is spring-loaded inverted pendulum. It's developed by Dan Kolicek, sitting here. Instead of restricting the center of mass in the plane, it has a swing mass dynamics. So these two models are probably the most common ones. Because their simplicity, we are able to achieve like kilohertz planing speed. But the downside is sometimes it's too restrictive for a certain set of tasks. That's why many people we can see in the literature try to extend from these simple models by adding an actuator or second leg, or use multi-linkage, or besides considering the center of mass, we also look at the inertia about the center of mass. So one big question that this thesis want to answer is, what is the best reducer model? And additionally, this extension that I'm showing you is limited by human intuition. So can we synthesize a reducer model that maximizes the robot performance? And kind of link back to the motivation slide. Currently, making a humanoid robot involves many trade-offs. We want to maximize battery capacity, but we want to reduce the weight. We want to increase the payload, etc. So being able to optimize the reducer model, or just in general optimize anything, can continuously improve the robot performance. Yeah. Okay. So the talk will revolves around reducer models. So here I mathematically define what I mean by reducer model. So here I'm showing you a full Ford model of a robot chassis. So the state and inputs are Q dot and U, and the trajectories here are other robots. Well, other trajectories that when robot accomplish some task, for example, walking at a certain speed. And we also have a reducer model. The state and inputs are y dot and tau, and similarly have the trajectories when it's doing some task. So I define my reducer model by a tuple of two functions. One is the projection functions that map the full configurations to reduced configurations. And the second function is the dynamics of the reducer model. So in the case of slip, the spring-loaded inverted pendulum here, The projection function is center of mass position, and the dynamics is the stream mass dynamics. Right, so with this in mind, here's the thesis outline. So the main goal is to find high performance reduced order models for Lego robots. In the first chapter, I'll look at a special case where I try to find an integrable whole body orientation for Lego robots. And in the context of the reduced model definition, I'm specifically trying to find the projection function, the embedding function, that optimize a objective functions that I will tell you later. And second chapter, I generalize to any objective functions and any task distributions when I look for the model. And lastly, I improve upon chapter 2 by incorporating reinforcement learning into the model optimization. Right. So first chapter, I want to start with a very simple concept, center of mass. Everybody knows this is the average orientation of a robot, and it has a very nice characteristics, which is it obeys the Newton's second law, right? F equals to ma. This is important because looking back to our definition of reducer model, we have the dynamics. So the F equals to ma is the reducer model dynamics. And we also have the projection, which is the center of mass position here. With these, we can plan with only the reducer model, right? We only look at the center of mass and looking at the external force, and we don't need to think about the details links of the robot, right? Those are abstract away during planning. And here I'm showing you visualizing the center of mass position for MIT Mini Cheetah. It's roughly around the torso. Nadia is similar around the torso, but on the right side here, so when Nadia shift to the left side, its left side, we can see the center of mass move correspondingly. This is the center of mass, everybody knows. Okay, what about orientation? We intuitively know, if we look at MIT Mini Cheetah, the orientation of this robot is probably well, if we use the base orientation, the torso frame should capture this orientation pretty well. For Nadia, well, when it's standing straight like this, using torso is fine. But when Nadia, let's say the upper body turns to the left side and maybe pitch forward a little bit, the base link orientation doesn't capture this anymore. So intuitively, we might have we can visualize probably this frame should turn to the left and then pitch forward too. So to find this average orientation, we have to start with things that we trust. In classical mechanics, angular momentum has very nice characteristics. We have the dynamics, the equation of motions of it. Yeah, we have the very nice characteristics. And one approach that Jordan's and some other researchers use is starting from this angular momentum. We define a angular velocity about a center of mass. And given this angular velocity, we can integrate forward in time and find the orientation. But there is a downside of this approach. This angular excursion can only be integrated numerically. There is no closed form solution, meaning that there doesn't exist a function, the embedding functions that I show you in the definition of reducer model that represent this orientation. So in our approach, we try to start with the embedding function. We call this integrable whole body orientation. And I visualize it using this WBO frame here. And the W frame is the world frame. So start with this orientation, this frame. It's a function of the joint positions. We can take time derivative to find the angular velocity of this frame. And then we can subsequently get the angular momentum approximated by this whole body orientation frame. And the goal is to find this frame that minimizes the angular momentum error. It has a couple benefits. So first, because we start with a function of a joint, so the integration of the velocity is history and path independent, and this orientation consider every orientation of the link, and also because it's a forward kinematics function, it's also suitable for the classical tools like inverse kinematics and task-based control. So yeah, to dig into the details, here's the problem formulation. So I already show you the frame, WBO frame, and the wall frame. Here I also visualize the frame B, which is the frame of the base. So QWB is the base orientation relative to the world. This we already know. We can measure this or estimate this using IMU, for example. And our goal is to find the orientation of the WBO frame relative to the base. And I use Q here because I represent this orientation via quaternion. And the quaternion has 4 elements, and we parameterize it using a pretty standard approach. We use a feature vector. And specifically, we parameterize only the last 3 elements of this quaternion, and we recover the first one using a constraint from unit norm of quaternion. And I already showing this, their real angular momentum and also the angular momentum approximated by the WBO frame. And the goal is to minimize the difference between these two. And if we look at the equations here, the only difference is the A and A tilde. And A is defined by M inverse, MB inverse and times MQ over there. I'm not showing you A tilde here because it's really messy. But what's important is A tilde essentially is a Jacobian of this orientation. And it's a function of the joint configuration and nonlinear in the parameters. So now we want to minimize the difference between the two. How do we minimize the difference between 2 functions? We use a pretty straightforward approach, which is sampling a bunch of configurations and then minimize the average error. So yeah, it's this problem, minimizing the average error of the 2 functions. And yeah, like I said, sample a bunch of configurations. In this case, n is equals 2000 configurations. And for basis functions, I pick just monomials up to 3rd order. And yeah, if we look at this problem, it's a nonlinear optimization problem. We can theoretically use any solvers to solve this problem, but we customize the solver that exploit the problem structure, and we found a solution within 2 minutes. So now, and now here I just show you the approximation, basically the fit-in result. So in the optimization problem, we minimize the difference between A and A tilde. And here I'm plotting A times Q dot, this term, and also the A tilde times Q dot. And we can see the difference is pretty small, approximated pretty well. If we look at the angular momentum, it's also, it fits pretty well. So yeah, now that we have this average orientation as a function of joints, I want to show you an application in task-based control. So this is a pretty standard planning and controller diagram in robotics. So normally we plan for desired trajectories given robot states, and then track these desired trajectories in a controller. In this example, I want Cassie, the robot Cassie, to follow a global yaw angle, which gradually turns 90 degrees over time. So one way to do this is to track this trajectory using the pelvis orientation. If we want to pick a link, pelvis seems like it's the best link to track this. And secondly, inspired by a human study, we found that when human walk, we normally exhibit fairly low angular momentum because the upper body motion cancel out the angular momentum generated by the lower limbs. And lowering the angular momentum also has benefits of decreasing the foot yaw moment. So given this, we would like to track this orientation using WBO frame, right? Because WBO frame is, it maximally approximates the angular momentum. So this is the result. On the left, the video on the left is the controller that you use the pelvis orientation. On the right is the one use WBO frame. So visually, the difference is not that big, but if we plot the angular momentum of the robot, we can see there is actually about a 30% reduction in the magnitude of the oscillation. And I also applied the same controller to Nadia, except Nadia has upper body, so I have to set a nominal pose for Nadia. And interestingly, when I do this, the upper body start moving pretty naturally when Nadia walk. It's because when we track this desired orientation, we also minimize the angular momentum, and the arm swing can do part of the job. Okay, and also I showed this on hardware. On the top here is the baseline controller, which fixes the upper body configuration. If we don't have any controller for the upper body, this is the standard. And the bottom is the WBO controller. We can see the upper body, not just the arm, but also the torso, also yaw. Right. So that was the first chapter. Okay. Now I want to generalize the model optimization to any objective functions and any task distributions. Okay. So in the motivation, I mentioned the model predictive control. And here is kind of the details of it. So normally inside this MPC, we have a reducible model planner that plans for the desired center of mass trajectories and footstep locations. And we have the controller that tracks these desired trajectories. And inside this planner, we have the reducible model dynamics G. And I also show you the embedding function that map the full configuration to reduce configuration in the diagram. And to remind you, my reduced model definition is the tuple of these two functions. So the goal of this chapter is to offline generate the model, find the optimal model, and then use it in the MPC. So in order to optimize the model, we need a metrics to evaluate the performance. And I use a cost function H. And so first I want to answer what is the performance of a robot completing a task. So I use forward model trajectory optimization. H is the cost function, and F is the constraints that includes the forward dynamics and includes forward dynamics, friction cone constraints, and many of the full model details. and I also have the task. The task here could be like walking forward with a certain speed. So the output of the trajectory optimization looks like this. So just walking forward with a certain speed. And now where's the reducer model? Reducer model comes in as additional constraints that forces the robot to behave like a reducer model. So R and G are the functions that I've been showing you. And once we added this constraints, the robot's motion looks like this. So for example, if we make the model LIP, then we can see it's so the resultant center of mass height is fixed in the plane. Okay, so now we have the cost associated with the reducer model. We can start optimizing reducer model. So this is what the outer loop optimization is doing. I have an expectation here because we do not just want the robot to be good at one task. We want it to be good at over a task distribution. And also to highlight, the task here can be anything, and the cost can be anything. Cost function can be anything. Yeah, now we have this bi-level optimization problem. How do we solve it? We solve it via stochastic gradient descent. And in order to use this algorithm, we need to derive the cost. And the cost can be conveniently derived using envelope theorem. So the gradient or the derivative is basically the inner product of the dual solution and a gradient of the cost with respect to the parameters. All right. So yeah, so initialize this to LIP. This is the motion. We can see the pelvis height is fixed. Center of mass, but pelvis is pretty good approximation for the center of mass. And after we optimize the model, we can see the pelvis can move a little bit more, and center of mass can move a little bit more. And yeah, so just to quickly highlight, this is the core idea of the method. So the constraint of the reducer model forces the robot to behave like a reducer model, right? And whenever we add the constraints in the optimization problem, the optimal cost goes up. And it's the outer loop optimization's job to update the parameters to minimize, to lower this cost. All right, so here I'll show you just two results. So I've done probably 200, 300 optimizations. Yeah, just to highlight just two here. This is the plot of the cost of the outer loop over iterations. And this cost is normalized by the forward model cost, which is the optimal cost of the inner loop optimization without the reducer model constraints. So the cost is bounded by 1, because the reducer model cannot do better than full model. Right, and in this example, the cost is a function of motor torque, and the task is a uniform distribution over stride length and body height. And yeah, we can see after a few iterations, the cost went down. And the second example here, the difference is the task domain. So in the first example, the task distribution is a uniform distribution between negative 0.4 meter to 0.4 meter. In the second example, we look at just the harder task. In other words, the bigger stride length part. And we see that the initial cost goes up a lot because linear inverted pendulum is not a good model for big stride length task. But at the same time, because the initial cost is high, it gives us more room to optimize to improve. Okay. And a couple takeaways. So the performance I've shown you here is task dependent And in other experiments, we also found that it's also cost function dependent. And to remind you that over the iteration, the model optimization, the model remains same dimension, but we get a better performance. And in this case, in the second example, we see like 40% of cost reduction. And yeah, it works. We observed that it works under different cost function, different tasks, and different robots. Here different robots. Theoretically, different robots, but in our experiments, we tried 2 robots. Yeah, and lastly, just highlight the planing speed. So besides the cost improvement, when we put this reduced model in an MPC, the planing speed is significantly faster, as we expected, than the planing speed using the full model. In this case, it's like empirically roughly 100 times faster. All right, so that was the offline model generation. Now we have this optimal model. We would like to use it in a controller. And hopefully we can see the same cost improvement. All right. So to kind of give you a little bit more details, the reduced model planer takes in task here. It could be walking velocity or the stride length, and also turning rate, ground incline. And it outputs the reduced model desired trajectories and also for step location. On the controller side, I have a time-based finite state machine and also a trajectory generating block. This trajectory generator, the job of it is to fill out the rest of degree of freedom of the robot based on some simple heuristics. And then I have a operational space control in the end, which track all the desired trajectories. So this is the results of the MPC. On the left here is the LIP. It's the initial model that we use. And on the right here is the optimal model. So the biggest difference that we can see from the video is the walking speed. And I also time how long it takes Cassie to finish each segment of the track. And on average, as shown in the table here, it walks 40% faster. And just to emphasize, this is real-time MPC. It's not forward model trajectory optimization. Yeah, so I will show you later how the model performs in terms of the cost function that I use during offline training. Yeah, so now Cassie is in the last segment. We can see for the optimal model, it climbs. Cassie can climb up pretty steadily, but on the left side here, linear inverted pendulum struggle. It cannot finish the task. All right, for time interest, I'll go to next. Cassie will eventually fall. All right, so this is besides the speed, I also want to show you how is the performance with respect to the cost function. So this is the simulation, right? This is not the offline full model trajectory optimization. So here, what I did was I run a lot of simulations with the MPC and also the reducer model, collect a lot of trajectories, and evaluate the performance of these trajectories using the cost function that I use offline training. So what do you mean by fire? Oh, it's the tasks that initially the initial model cannot do, but so it would be in this case, Cassie can walk up 50% incline with the optimal model, but LIP cannot. So I claim this task is acquired. That's what I mean. Yeah. Right. So yeah, so the plots here, they're both showing the cost ratio of the optimal model to LIP, the initial model. So if the value is equals to 1, it means that the optimal model performs as well as LIP. If it's lower than 1, it means the optimal model performs better. And we can see for the task regions that I show you here, optimal model performs better than LIP everywhere. And specifically, we can see the optimal model improved the cost by 23% for the negative ground incline task. And yeah, and the green area highlighted the acquired task, like I said earlier. And just to put this into context, for some for a specific ground incline, you can see up to like 50% of faster walking speed or bigger stride length. And lastly, I also show you the training task is highlighted by the dash line box. And we can see in this slice of task, the turning rate and stride length, the optimal model can still perform pretty well outside this box. So it generalizes pretty well to unseen task. Okay. And hardware result. In order to put this on hardware, we added some heuristics to maximize to improve the robustness. Specifically, we improve it via restricting the center of pressure at the center of the foot. This does hurt the performance improvements. As we can see, instead of 20%, we only see 10%. But it improves across the trajectory optimization and simulations and hardware. And just a remark, we found that LIP is actually a pretty good model for CASI because the mass is pretty centralized in the pelvis, in the pelvis region for CASI. And the feet are pretty light. For example, it has line feet instead of a finite size feet. And we did a few experiments to try to optimize the model on a different robot model. And we found a much better improvement. So we expect that if we put this on Nadia, for example, we can see much better improvement. Okay. Yeah. So in chapter 2, we automatically synthesize the reducer model that maximize the performance. This performance is evaluated by a user objective functions, and also we optimize the model over any task distribution. And now I would like to incorporate the reinforcement learning to further improve the model performance. Okay, so start with the problem statement. The goal is similar. Well, actually, it's the same. We want to minimize a cost given a task distribution. In the previous problem, so this is the previous problem, right? We minimize the expected costs. And this cost is a function of task and the model parameter. And specifically, the cost is actually the optimal cost of a forward model trajectory optimization. And yeah, I use the cost function H. This cost function is evaluated over the trajectories inside the trajectory optimization. One issue that I didn't mention was that, well, I didn't mention explicitly, was that this optimal policy is not computable in real time. So if we want to put this on a robot, we have to find an alternative policy. In the previous chapter, we used an MPC as this policy. So this gap in policy can actually cause a potentially a gap in the performance too. So the costs might not be different depending on the controller heuristics. So in this chapter, we would like to use this online MPC during model training. Right? So we do not use optimal control offline anymore. We use this MPC. And yeah, it roughly looks like this. So this is the same MPC as the one that we use online. And we train it in simulation. And so we basically run a lot of simulations, collect data, and given this data, we optimize the model parameter. So now I have closed loop performance to closed loop performance. There's no gap. And this, so the change between the previous problem to the new problem looks pretty simple, but this actually make this a reinforcement learning problem. So yeah. So here is the structure details for the reinforcement learning problem. So this is the MPC, the same MPC that I showed you earlier. Now we have a robot simulator to close the loop because we're training in simulation. So in our RL formulation, we pick the planar to be the policy. So the parameter of this policy is the parameter of the reducer model inside the planar. And everything else constitutes the environment inside this RL. So we run, like I said, run a lot of simulations, collect data, and update the model parameters. In this case, it's the model parameters inside the policy or the reduced model planar. Okay. And the goal is to minimize the cost function H given task distribution. Well, in RL, instead of minimizing the cost, we want to maximize the reward or the return, which is the collected, the accumulated reward over time. And the reward function that I use is this. So W's are the constant weights. The first term encourage minimizing the costs. And the second term encourage completing the task, right? So this is the RL problem that we want to solve. We can solve it using many solvers. In our example, we use CMAES, which is a evolutional strategy method. And in this method, we basically sample the parameters via a Gaussian distribution. And also in our experiments, we found that optimizing this reward over a very big task distribution or a task region is a very hard problem. It's very hard for us to get a good model. So we employed curriculum training where we start with a smaller task region and gradually grow it over time, over the learning iterations. And specifically, I discretized the continuous task domain into a set gamma D and gradually grow this set over time. Okay, so we optimized the model in a simulation, and here are the results. First, compare the optimal model to the LIP. This is also the cost ratio plot over task that I show you in the second chapter, but for a different optimal model. So we can see up to 21% of cost reduction, and also see a pretty big, actually, yeah, a decently big growth in the viable task region size. And we also want to compare this optimal model to the optimal model that we derived in chapter 2, right? So we can see, besides a mild improvement in costs, there's a pretty big task regions growth, meaning that the optimal model that we derive in this chapter is capable of completing more tasks than the optimal model that we derive in the previous chapter. And besides these numerical results, I also want to highlight that this new approach is easier to implement because we don't have full model trajectory optimization that we have to implement. And also there's no open loop to closed loop gap that I showed you earlier. And lastly, using the RL approach, we can make the model, we can use the model with very high fidelity, as high as we can, because we run simulation. So the details in this case could be, we can add like the actuator delays, we can add state estimator, we can add compliant components of the model, which might not be easy to add in the previous approach because having a very complex model inside forward model trajectory optimization make it very hard to solve. Okay, so that was the last chapter. In summary, this thesis, this is the first step towards finding a high performance reducible model. We formalize the measure of reduced model capability and directly optimize it with respect to a user-defined objective function. The framework is general to any objective functions, any tasks, and any robots. And it has implication in, well, potentially over the whole robotics field. And yeah, specifically in the first chapter, I found the whole body orientation. It's a function of, it's a forward kinematic function that maximally approximates the real angular momentum. And in the second chapter, I optimized the model with respect to any cost functions and any task distribution, and embed this optimal model in the robot via MPC. And lastly, I incorporated RL to further improve the model performance. Okay, so future work, what's next? So because last chapter, we turned the problem into RL reinforcement learning problem. Some people might ask, why not just use full-on black box reinforcement learning method? Well, even though it shows really good performance in specific tasks, there's one downside, which is the task-based parameterization is determined during training. So what I mean by this is, let's pick the bottom right policy. So the neural net takes XY positions as an input. And if we want the robot to walk at a certain speed, we have to augment it with velocity commands and retrain the neural net again. And we argue that there are many conceivable tasks that we want a robot to do. So it is practically infeasible to list everything beforehand. On the other hand, a model-based approach can simply add a new task as a constraint inside the MPC, so it's much easier. And also the model, what is this? You haven't finished signing. Okay. Right, sorry about that. Right, the model-based approach, we have a model, we can interpret it, and we can apply classical tools to guarantee the safety and stability. So in our last chapter, we actually did this already. We combined model predictive control with reinforcement learning to derive a physically interpretable model that maximizes the performance. But we think there's still much more to explore here. And I want to emphasize that. So this might look like it's a model-based RL, but it is not exactly, because in a conventional perspective, we minimize the modeling error. But in our approach, we actually want to maximize the performance, right? We don't minimize the modeling error. Yeah, and in other words, we explicitly optimize over model, but also implicitly optimize over the control policy. So the model actually encodes the control policy. Okay. Yeah, so that was the first feature work. And the second feature work is, let's look at the reduced model definition that I had. So I have this projection function and also continuous time dynamics. But leg locomotion inherently involves hybrid dynamics. So we don't have the discrete time dynamics here. We actually circumvent this problem in the MPC by assuming zero impact, ground impact, a foot touchdown event. So yeah, so there's the future direction that we can go. And yeah, the third is it'll be interesting to apply the stability and safety guaranteeing tools to the high performance model that we just derived. If we want to have humanoids to work around humans, humanoid robots to work around humans, we do not just want the robot to be like safe by itself, but also we don't want it to do something unexpected to hurt the humans around. And yeah, lastly, we found that in our experiments, linear models surprisingly did very well in a specific set of tasks. This is pretty exciting because, like I motivated in the first slide, making a humanoid robot involves many trade-offs. If we can improve, so if we use linear model, right, then the MPC problem becomes a convex problem, and this significantly reduce the computational needs. Right. So finally got into an acknowledgement page. First, I want to thank my advisor, Mike Posa. So there are many things that I want to thank Michael. There's too many things, but I want to thank him for showing me how to think like a researcher. He showed me how to solve a problem. And yeah, I've in the PhD journey, the entire PhD journey, there are a couple times that I thought to myself, what a pleasure to have Michael to back me up many times. It feels, I feel safe under Michael's guidance, specifically in the beginning phase of my PhD. I can remember my first conference talk. I was actually very nervous on the stage. There is the recorded video. But when I saw Michael sitting in the audience, I remember that we went through many practices and that calmed me down a lot. And that is probably how I finished the talk. I don't know how it went if Michael didn't sit there. But yeah, there are many things that I'm grateful for. And I also want to thank committee members. Thank you for being a part of the committee, providing constructive feedback and ask very good questions to me. And collaborators, I want to shout out to Gabe. Thank you for teaching me what is whole body orientation and giving me the opportunity to continue your project. Also, their lab members. So I hope you hide behind me, so I put your photo there. So yeah, many people I want to thank, specifically Will and Brian. Thank you for, I guess, accepting Michael's offer so he can work on Cassie with me. Working on Cassie is definitely not one-man projects. Like building the state estimator and the controller, just everything from scratch is it's probably gonna take 2 more years from me. I don't know. But yeah, I'm very grateful for having you on the same team. And thank you, Wanxin, for teaching me envelope theorem. Thank you, Ken, for teaching me reinforcement learning. Thanks, Matt, for sharing the job hunting experiences. There's so many things I want to thank to many people. But yeah, thank you for being a part of my journey. And I also want to thank many members in Boardwalk Robotics and IHMC. So particularly Jerry, thank you, Jerry, for giving me the intern offer, giving me the opportunity to work on Nadia robot. It was probably I shouldn't say the best summer that I had during PhD, but I kind of feel so. I was really happy. I feel like every day, it's like I feel it's like party there, just every day. I don't know how to describe, but everybody like playing around, just so fun. And I also want to thank Robert for many discussions when Jerry and Gabe went for starting another company. Yeah, I needed those discussions, and also thank the hardware team. I remember Brent, not Brent, Brandon. I think we broke the robot at 5 p.m., but we have like a deadline. I think you came in after 6 p.m. to fix the robot so that we can use it the next morning. I'm very grateful for that. And thank you for Nomi and many people that show me how to use the software there too. And lastly, coming to US to study is not easy, particularly during COVID time. I'm very grateful to have you around me to support me during the difficult times. And yeah, I cannot conclude. Well, I just want to thank my parents. You probably don't understand what I'm talking now, or if you watch the recording, you probably don't understand what I'm saying. But I'm so thankful that I have you. You always support me in whatever I want to do. And also my wife, lastly. You always take care of me. Without you, I'll probably be a different person, a worse kind of person. So yeah, for example, you always take care of me. Like this morning, you know that I'm practicing my defense talk. I'm preparing the slides, and you notice that I haven't had breakfast. So you prepared breakfast for me and put it on my table. And all those kind of details, I'm very grateful for. Yeah. So yeah, with that, I can take any questions.